So it's not going to be of a musical, but there is going to be music infused in this because two of the things that I love best in the world is physics and astronomy and music. And so this is my little experiment today to try to do a talk that infuses those with one another. So show of hands, who in here is interested in astronomy? Awesome. Who in here is interested in music? Okay. Who in here is interested in physics? All right. Well, this is going to be a non-technical talk today. So I am going to talk about some really cool details about the life cycles of stars. I find the life cycles of stars fascinating, and I find that what goes on with stars, well, we may think of them as being very far away, and they are very, very far away. And we may think of them as being very, very different from us because they last a really long time compared to us. I mean, we might make it to 90, 100 something years old, maybe. But when we're dealing with stars, even the high mass stars that burn through their fuel really, really fast are going to be doing that for about 1 million years. And then those low mass stars, oh my, I mean, 100 million years or more that they could be doing their thing. So we're going to be talking about a little bit of all of that today. And
you're good.
Good?
Yep.
Thank you, Cody. I appreciate it.
Yep.
All right. So the picture that you see on the screen has become a pretty famous picture. What you're seeing here is a stellar nursery. These are called the pillars of creation. The pillars of creation are found in the Eagle Nebula. And if you want to go out and look tonight and see if you can find out where the Eagle Nebula is, you're not going to be able to look, I don't care how good your telescope is, and see this. But if you want to look toward the Eagle Nebula, you might be able to make out a fuzzy patch if you have a good enough telescope. And you would look in the constellation Serpens Cautis. And I can say right now, Serpens Cautis is not the most famous constellation you have ever heard of. It actually looks like a few little dots that you can kind of make into a line with your eyes. Saddest looking snake I think I've ever seen. So instead, you might want to look for the constellation next to it. The constellation next to it is called Ophiuchus. Ophiuchus is actually the 13th zodiac constellation that never really got included, but it is one of the constellations the sun passes through over the course of the year. And I find it easier to look for because to me, it looks like a child's drawing of a house. You know, you've got the walls and you've got the floor and you've got the roof, and it's not really square. So the signs are like, the signs are different sizes. If you can't find that, just below Ophiuchus, there's the constellation Sagittarius. Sagittarius looks straight up like a little teapot. And it's in the southern part of the sky. Right beside it is Scorpius. Scorpius looks like a J with a line across the top because it's supposed to be a scorpion, right? So if you have an interest in looking for that in the night sky, I know that inset is pretty tiny. You can see that. Now, these two pictures, what made them so famous is first, the one on the left was made by the Hubble Space Telescope in 1995. And before 1995, we knew that dense clouds of gas and dust in the universe could form stars. But we didn't know very much about that process. And so one of the things that was discovered when Hubble first gave us this photograph is that we could actually see detail never seen before. And within these columns that are made up of dark dust clouds, we're seeing regions where there are dense regions of gas and dust that are not only dense enough to come together because of gravity, but they meet another very important criteria. It's cold enough in there, and they are protected enough from the ultraviolet radiation of other stars to start forming protostars. If they were left out on their own, the other stars would eat away all of their material before they ever had a chance. And so we're seeing here protected areas. Now that left image, the first one, the Hubble Space Telescope made in 1995. In 2014, it went back and with updated instrumentation, made the actual picture that you see here today. So this is actually better than the one from 1995. And then the one on the right, it's getting all the fame and glory right now because that is the one that was made by the near infrared camera on the James Webb telescope. And we did get a lot more clarity. Now, this is just supposed to be about an hour today. And there are many, many, many more constellations in the sky and way, way many more stellar nurseries. See the Eagle Nebula here? I'm mentioning one of them. This is the Orion Nebula. It's probably most famous for the fact that it's in the constellation Orion. And how many people in here can find Orion in the night sky? See a little of this going on. Orion has telltale sign in that there is those 3 belt stars. If you can find the 3 belt stars, you're probably good to go. If you find those 3 belt stars, which are actually very bright compared to the other stars around it, and you want more confirmation, in Orion's shoulder, you'll see a star that looks a little bit different color than the others, sort of a little bit of a yellowish, reddish, orangish. That star is the star Betelgeuse, and Betelgeuse is a red supergiant. In fact, if Betelgeuse were where our sun is right now, it would engulf Mercury, Venus, us, and Mars. We would be inside it. So that's how much bigger it is than our sun. If you're still not satisfied, there's another really bright, important star in Orion's knee. And there in Orion's knee, you see the constellation that is a bright white blue supergiant, Rigel. Now, the nebula itself, if you see pictures superimposed onto the constellation Orion, you'll see that hanging off Orion's belt is either a sword or sometimes an axe. It depends on what the artist's interpretation of it is. But there at the bottom of it, it's in that region that you would find the Orion Nebula. And the Orion Nebula is a region of space that has been giving birth to new stars, thousands of new stars, for a very long time now. Now to get into the music piece of things. When it comes to looking at the stars in the night sky, we all have our different interpretations because we all have our own different human experiences. Different things we're going through at different times, different things that we see, different interpretations. And probably the first time that I realized that I could bring music and astronomy together in some way is when I was in elementary school. I grew up in a little town in Arkansas, and I had the coolest music teacher in elementary school. Her name was Miss Dunn, and Miss Dunn looked like a Barbie doll. And she went to Jonesboro and she played jazz music on the weekends. And I thought, wow, I don't know what jazz music is, but that sounds pretty cool to me. So one of the songs that she introduced in our class, and I think that maybe other Gen Xers in here might have heard this in their music class, maybe some of the boomers have heard it in their music class as well, is a song that's called Orion is Arising. Now it's hard to find this on the internet. But it's written by James Zimmerman, and I can only find that it was recorded once by a particular trio. And I'm going to share it with you. And if you know it and you want to sing along, you can. Orion is rising. You can see his stars blazing in the middle of their country sky. And it's not too surprising that the sky is still amazing way out here, but nothing hides it from our eyes. And sleeping outside in a boat to the kid seems like the best thing that I ever did. And chasing the shadows and the tracks in the snow. Don't you know? Orion is the rising. You can see his stars are blazing in the middle bright tree sky. Writing music, there are lots of things that you need to think about, but you don't need to. You can just write whatever you want. You can plug your Bluetooth and play to your heart's content. But some of the things that songwriters think about is, what's the rhythm going to be like? You know, what's going to be the beat? Is there going to be a beat? What's the key signature going to be? There is a composer from Russia, and he was popular around the time of the Tsars and the Revolution. And it was his contention that different keys, different music actually corresponded to colors. And so when he wrote music, it corresponded to color, something that you could use other senses for. It may be that there is a certain chord progression. And as you listen to some of the things that I played for you today, I'd like for you to think about those things, think about those chord progressions. And for those of you who are not musicians, here are 4 different chord types that I think are interestingly placed, especially in music that is written about or for and inspired by stars. So here's a major chord. Nice, happy, bright major chord. Here's a minor chord. A little sad, a little more downbeat. If you really want to get downbeat though, you make that minor chord into a diminished chord. Get that villain and railroad tracks feel going. And then there are the augmented chords. It's nice to sit with and think, how does that make me feel? How does that relate to what I sing? How does that relate to things that might be going on in my life or in something that I'm trying to describe? So I'm going to play for you now something that is very, very different from Zimmerman's work, but that is inspired by Orion as well. And I can see Brian is just about to wiggle out of his seat because he knows what's coming. Now, this is an 8-minute song by Metallica. It was written by their bass player, inspired by Orion. And one of the things I want you to look for, maybe not at first, because there's some traditional guitar work at first. Then there's a lovely bass solo. That's right, a bass solo in the middle of it. And he used this wah-wah pedal to get the nice spacey effect. And so if you don't know what a wah-wah pedal is, look it up, that's fun.
It's a commercial.
Do I have to play the commercial?
Tell me a website you love with Wags. Where your words.
There we go.
And if you have a hair tie-in, you might need to take it out to properly enjoy the first part. Can you begin to hear it?
Will be.
Are we ready? It starts solo. Later on, but really nice today. Yeah, so give me that. Notice how they take the rhythm up. I'm going to have to take right to the time, right? It's I'm gonna skip ahead again. Really crunch it. Probably this one. But certainly, it's pretty easy to contrast this with what James Zimmerman wrote in the 70s. Although, I gotta say, I didn't do the second verse. There is a second verse. It gets a little darker than the first verse, but probably not as dark as some of the parts of this particular piece of music. And I say that a full well knowing that this piece of music by Metallica does not have any words. It's a music, it's an instrumental the whole way through it. Now, I talked to you a little bit about what it takes to make a protostar. You need gas and dust from interstellar space. It needs to be dense enough and it needs to be protected enough so that it can form a protostar. And protostars are what you get when that gas and dust gets to come together, gravity pulls it together, so much so that instead of being a transparent gas, it is opaque, so you can't see through it anymore. And it becomes spherical because any object in space that is over a certain amount of mass will form a spherical object because that is the most advantageous for gravity. It's the lowest energy state to make it spherical. It gets all the particles as close to each other as they can possibly get. And when a star is doing all of these things to become a protostar, friction heats it up inside and it begins to get hot. Now, if it gets hot enough, then in the core of the star, fusion reactions can begin. Now, for stars that are not massive enough for this to happen, they never have fusion begin in their cores and they become what we call brown dwarfs. Really hard to find. But if fusion does ignite in the core, this is a super duper, very energetic thing. And what it's going to do is it's going to cause the star to swell up. And so the star is going to swell up because there's this really energetic reaction that's happening inside it. But it'll only go so far, and then gravity says, no way, get back in there. And so gravity pushes it back in again. But gravity pushes it too far, it's too hot inside, and it pushes back out. And this pulsing will begin once the protostar starts the fusion reactions and becomes a star. And this dance will go back and forth until the star becomes stable. Now, another thing that's happening that I want to tell you about that has to do with the fusion reactions is related to this picture that you see on the left. That is the kind of fusion reaction that's taking place in the core of our sun right now. But a special kind of fusion reaction that takes place at about 10 million Kelvin. 10 million Kelvin hot. And it is a multi-step reaction that turns hydrogen into helium, and in the process of doing so, it creates antimatter that goes on to hit electrons. And when it hits those electrons, it forms gamma rays. And there are also neutrinos released in the process. So there's a whole bunch of things going on. So that even though we can't look at the core of our sun to see what's going on, we get those neutrinos. In fact, they can pass out of the sun and be to Earth within about 8 minutes. And we're looking at what process is going on in the sun. How many neutrinos are we getting? What does that look like? We also get the photons, or the light particles. But it takes a long time for the light particles to get out because they have to pass through the non-burning layers. So the light takes a little longer. But yeah, this is the proton-proton chain. Now, I'm going to show you one of the, probably the most important diagram in all of astronomy. So exciting. This is called the Hertzsprung-Russell diagram. Who would know something so simple could have told us so much about stars? Now, this is like a graph, as you can see. Along the horizontal axis, that's temperature. Okay? From hottest on the left to coolest on the right. On the vertical axis, that's luminosity, measured in watts, just like your light bulb is measured in watts. There's 40-watt light bulb, 100-watt light bulb, a 200-watt light bulb. These are just much, much bigger wattages. When astronomers started using this diagram and mapping out the stars on here, so putting them where they should be based upon their temperature and their luminosity, they found that there were some undeniable patterns. One of the big patterns that you see, I know it's not that it just looks like a rocket ship, is that from the top left corner to the bottom right corner, that's where almost most of the stars fall. And so that came to be called the main sequence. Now, we also see a pattern that along the main sequence, the stars that are most luminous are the ones that are also the hottest. Also along the main sequence, the stars that are the coolest are the least luminous stars. So there's a relationship there between temperature and luminosity. So let me get off to a couple of the other regions that are there. They're undeniable. One is in the top right. There are stars in the top right that are obviously cool stars, but they're just as luminous as the hot stars. How does a cool star get to be as bright as a hot star? Has to be really big, okay? Like Betelgeuse in Orion. And so those stars came to be called giants. Some of them get big enough that they're called supergiants in that part of the diagram. Then in the bottom left, we've got stars that are really, really hot, so hot that they glow white blue. But they're not very luminous. So if you think you know why a hot star would have a low luminosity, raise your hand. Why would that be?
You said before that sometimes light has to get through and it's going to have trouble getting through.
That's a good thought about something that goes on in the core of a star, but for a whole star, if the whole star has a really high temperature, for it to maintain a low luminosity, it needs to be small. It needs to be a very little star. And that's why that region of the graph is called the white dwarf portion. This diagram here, we can use to trace out the life cycles of stars. And for stable stars, they are stable stars and are graphed on the main sequence part of this graph for most of their lifetime. That's why so many stars are there. They spend most of their lifespan turning hydrogen into helium, and so they show up on this part. Then, as they start running out of hydrogen, they're going to evolve into the red giant, supergiant region, and maybe eventually down to the white dwarf region. Our sun is a low mass star. Low mass stars are any stars that have less than 8 times the mass of the sun. Our star is also a G2 spectral classification star. And so it's right about in the middle of that main sequence that we just looked at. With low mass stars, once they run out of hydrogen in their core, there's a buildup of helium in the core. And then hydrogen fusion stops. And the star will begin to contract. Gravity takes over, gravity starts to win. If gravity can get the temperature of the core up to about 15 million Kelvin, then a more energetic process that turns helium into carbon can begin. And for a low mass star, it might even get to the point where it can turn carbon and helium into oxygen. But at some point, it's not going to be able to cause any more fusion reactions. So gravity's going to take over. And when gravity takes over, it's going to cause the core to very rapidly shrink. And it shrinks so rapidly that it leaves behind the layers of material that it's formed. And they don't have that gravitational pull as strong as they did, and they start to just move out away from the core. And when they do this, they form an object called a planetary nebula. Planetary nebulae are beautiful. This one in particular is the Ring Nebula. And you can see that there are different colors, and those different colors can correspond to different temperatures of the nebula. Because they're nebulae, because they are very diffuse gases and they're being heated up by something that's really hot, they will glow in the visible part of the spectrum so that you can see them in these different colors. The name is awful, though. They were named before anybody knew what this process was, and the people who named them said, oh, it's a nebula. At the time, anything that looked fuzzy in your telescope was a nebula. Even comets were nebula, because they were fuzzy things in the telescope. So there's no stellar birth taking place here. The other thing is, around the time that they were naming this, they had found Neptune and Uranus, and they were looking at the colors that they saw in Neptune and Uranus. They're like, oh, those are planets. That's kind of a planetary color, called a planetary nebulae. Name stuff, but this is actually an ending point for the star. All right. So what happens to the core? The core, since fusion reactions can't begin, it's going to contract and contract until something stops it. And it turns out that with a star whose core remnant has about 1.4 times the mass of the sun, or less, electric forces can stop it. So atoms get packed together so tightly and electrons get packed together so tightly that they just can't get any closer together. And so we end up with a new form of matter that our white dwarfs are made of. We call it electron degenerate matter. So you've got solids and your liquids and your gases and even your plasmas. This is a dense, hot form of matter that is so dense that if I had 1 teaspoonful of it, 1 teaspoonful of this electron degenerate matter would weigh as much as an adult elephant. What? That's right. 1 teaspoon. So this is an incredibly dense kind of matter. Also, we had something that was as big as our sun, maybe even bigger to begin with. But if you look at the picture up here, you'll see that our picture of a white dwarf compares it to the size of the Earth. To give you a little more context, you can fit more than 1 million Earths inside our sun. And so here we've had a case where something that was as big as our sun or bigger has shrunk down to the size of the sun. So it's gotten more than 1 million times smaller. Now, since I broke this up into talking about low mass stars, now I'm ready to talk about high mass stars. With high mass stars, they have a lot more fuel, okay? They've got large masses, they've got lots and lots and lots of hydrogen, maybe some helium, some dust, and some different things thrown in, depending on what generation star it is. But they have to contend with gravity. They're more massive, so gravity pushes on them harder. which means that they have to burn their fuel faster. They have to have more energetic interactions in their core to fight against gravity. And because of that, even though they have more matter, they burn through it faster than the low mass stars. So whereas a low mass star might last 10 billion, 100 billion years, high mass stars might only exist for 1 million years, 10 million years, maybe 100 million years. So live fast, die young kinds of stars. Metallica should have written a song about them, right? Now, while they are in their main sequence lifetime, though, because they're maintaining this very large energy output, they have higher temperatures in their core, and so they can not only turn hydrogen into helium and helium into carbon and carbon into oxygen, but they can also turn oxygen into even heavier elements all the way up through the element iron. And I'm going to come back to iron in a minute and talk about why that's important. But these are some differences between high mass stars and their life cycle and low mass stars. Fun fact about iron, getting light to you. Fun fact about iron, it's element number 26 on the periodic table, and it has the most stable nucleus of any element on the periodic table. Its nucleus is so stable that if you try to fuse iron, that interaction takes more energy than what you have. And so when a star gets to the point where it tries to fuse iron, it's going to suck up energy, and it's going to help gravity in trying to collapse it, which means that the stellar core, when a high mass star gets to that point, is going to shrink very, very rapidly, so rapidly that it rebounds. And when it does, it sends shock waves through its outer layers. And all of those outer layers of all of the elements that it's been making since it became a star shoot out in all directions. And while they do that, that means that they are enriching the interstellar matter with all of the elements that they made. Plus, they release a whole bunch of neutrons, little neutral charged particles. And these neutrons can sneak into other atoms that are trying to escape. And when they sneak in, radioactive decay processes take place, and that helps to form other elements, all the way up through elements like uranium. Okay? Now I'm going to show you a couple of videos about the Crab Nebula, which is the nebula that we're looking at here. For any artists in the room or photographers, especially astronomy photographers, this picture is a composite. And so they did what astronomers do a lot of the time, and they took the picture of the Crab Nebula in the same way through like a red filter, and then a green filter, and then a blue filter, and actually other filters that are in different parts of the spectrum, like the radio part of the spectrum, the X-ray part of the spectrum, and then superimpose those onto each other to get this very detailed, high-quality photo that you see. And note the music they put with it. So some nice high organ sounds, some ethereal sounds, but a nice kind of kick beat at the bottom of that. So here is what they think that it looked like when this star went supernova. Notice how it became a red giant first. Becomes incredibly, incredibly bright. Becomes a huge neutrino source. And then eventually settles into what we see now. Now, that tells us what happens to the outer part of these high mass stars when they run out of fuel in their core. Well, what about the core that's left? Well, the core that's left when you have a high mass star, if it retains between 1.4 and 3 times the mass of our sun, then gravity is going to take over and it's going to shrink and it's going to shrink and it's going to shrink. And this time, not even electric forces are strong enough to stop the collapse. So what is strong enough to stop the collapse? Nuclear forces. So it turns out that this time nuclear forces have to stop the collapse. And as a result of that, what happens with this neutron star is that it becomes a collection of nothing but neutrons, the neutral parts of atoms. Any protons and electrons, they get squeezed in there and they become neutrinos and they emit positrons, which are antimatter, but that's what happens. Which means that this is even more dense than the white dwarfs. So what do you think a teaspoon of a neutron star might weigh?
Like 1,000 elephants.
1,000 elephants. About as much as a small mountain. Pikes Peak in a teaspoon. So this is incredibly dense material. And also, I want you to notice, because this can be deceptive, the picture on the right is a picture where they're showing a star field and a neutron star. And they've got a little arrow pointing to it because it's teeny tiny, right? Thing on the right side of the screen, the really big thing, that's a white dwarf. That little thing up there is the neutron star. So whereas a white dwarf might be as big as the Earth, a neutron star is going to be about 10 kilometers across, in other words, about 6 miles across. So we could put it between us and Pittsburgh. I wouldn't recommend it. Now, most of the stars tend to have magnetic fields. And when they collapse, those magnetic fields get stronger. Also, most stars spin. Our sun spins once every 27 days, which is pretty rapid for something as big as that. But what happens when an ice skater is spinning? They have their arms out, and then they bring their arms close to their body. They start spinning faster. Same thing happens with stars. So a star that was spinning pretty fast to begin with, when it becomes a neutron star, it's really spinning very, very fast. And when you have a combination of a strong magnetic field and something that's rapidly rotating, you get this dynamo effect that creates radio pulses. And so some of the neutron stars become pulsars. Now, the ones that we call pulsars are the ones that form in such a way that they sweep radio waves past our planet. Those radio waves can be turned into sound waves in the same way that we take radio waves from a radio station and turn them into sound waves in our car. But I'm going to go on to the next slide and I'm going to let you listen to a couple of pulsars. Okay. That's PSR B0329 plus 54. Catchy name. This is the crab pulsar, but this has been slowed down because at its original frequency, it just kind of sounds like a bunch of noise. So this is slowed down a little bit. Now, what if you took the sounds from a bunch of pulsars and superimposed them on top of one another?
Dance music.
We're about to find out. Slow sound. So when I slow down, it's to hey, what do you think? Very nice.
Nice.
Doesn't get a lot of radio time. But... All right. What happens when you have a stellar core that has more than 3 times the mass of the sun? Nothing can stop the collapse. Gravity takes over, gravity wins, gravity smushes it. So that you would have 3 times the mass of the sun, 100 times the mass of the sun, millions of times the mass of the sun, because there are supermassive black holes that are squeezed into a region smaller than the head of a pin. That's like a sewing pin. Now, because of this, that small, very, very dense region in space, we call it something, we call it a singularity. And that singularity is then surrounded by something called an event horizon. Here's how an event horizon works. You have a singularity with an event horizon. Remember, this thing was once a star, maybe a collection of stars. And so you can orbit it. So you can take your spacecraft out and you can orbit around it. Planets can go around it, moons can go around it. If you want your spacecraft to escape and get away, as long as you are outside the event horizon, you can still do that. But if you cross the event horizon, you are never going to get out of there. You cannot possibly go fast enough to escape a singularity once you pass over the event horizon. In fact, the thing that travels the fastest in the space of our universe, which is light, can't even get up enough speed to get out of that black hole once it's crossed the event horizon. And that is why it's called a black hole. Now, what can happen is that you can end up with light that is circling. You can also end up with accretion disks. This is disks of material that's moving so fast that it gets really, really hot and it glows. And so what you're seeing here, really big deal, just happened a few years ago. This is the first ever actual picture of a black hole. And this black hole is at the center of our Milky Way galaxy. So it's only about 25,000 light years away. That, of course, means we're seeing it right now as it was 25,000 years ago. But stars live so long, that's not very long to them. That's just a long time to us. And there are so many things. I could do an hour just on black holes. But a couple of things I want to point out that you might not have heard of before. Initially, the study of black holes were all about studying stationary black holes, non-rotating black holes. But if when they were stars they rotated, why wouldn't they rotate when they're black holes? And so they started looking at rotating black holes. And what happens if you have a black hole that rotates? It brings its event horizon closer and closer to the singularity, so that if it spins fast enough, it might be possible to have a naked singularity in space, which means you could just be doodly-doo-doo-doo, and you don't see an event horizon because the event horizon has shrunk so much, and then there you go, you're in the singularity, the black hole's gotcha. So I think that that's fairly interesting. Another thing that I find very interesting that is a more recent discovery, and more recent, it's been the last couple of decades, but Stephen Hawking, he and Penrose, they argued about the parameters of black holes for a long time. But one of the things that Hawking discovered that happens at the event horizon of black holes is related not just to general relativity, which is what we use to describe the behavior of big, massive things like this, but it's also related to quantum mechanics. Turns out that at the event horizon, the vacuum of space can be manipulated in such a way that energy, pure energy, gets turned into a particle and an antiparticle. So you have the creation of matter and antimatter at the event horizon. Part of it falls back into the black hole. Part of it stays in the universe accessible to us. And it is because of this that he thought that it was possible for black holes to eventually evaporate. Now, it would take a very long time for that to happen. But yeah, basically it's just the application of the old E equals mc squared. Energy is equal to mass times the speed of light in vacuum squared. Mass can be turned into energy, energy can be turned into mass, and that seems to be happening at the event horizon of black holes. So this is the summary of what we've talked about today. But one of the things that I find super interesting, I know I kept talking to you about chemistry along the way too. I was like, why are you telling me about all these elements? Yeah, there's the carbon and there's the oxygen and blah, blah, blah. Where do the elements that our planet is made of come from? There is no biological process. There is no geological process that creates elements. All of the elements that make up our planet came from stars. When we look at our sun is a middle-aged, middle-of-the-road, low-mass star. But when we look at it, we look at its spectrum and we see lines that indicate that it has iron in it. And we see lines that indicate that it has carbon in it. So that means that our sun has within it elements that not only is it incapable of making, but that it's far too young to make, even if it was massive enough to make it. So where did the sun get that stuff? Well, remember I said that when a star goes supernova, it throws all of these elements out. And so all of that stellar nucleosynthesis, all of that supernova nucleosynthesis, it enriches the interstellar medium. And it makes ways for new stars to be born that have these elements in them. And if these new stars in their process end up with planets, that's where those elements for those planets come from. Now, I'm pretty sure that everybody was born and raised on this planet. If not, tell me later. But that means everything that we're made up of, all of those elements, all of those atoms, they came from a star, maybe 2 or 3 stars. There could have been 2 or 3 supernova explosions that happened in this vicinity before our sun and our solar system came about. So literally, the iron that's in your blood came from a star. So that's one of the really personal notes for me that helps us relate, or helps me relate to the stars, and makes it very important for me. Sure, your body has cells, the cells die, and you get new cells, but you don't get new atoms. I'm breathing out atoms, you're breathing in those atoms. You're breathing out atoms, I'm breathing in those atoms, and they become part of our body, and it is a way that we are literally connected and bound together pretty strongly. So, that brings me to the finale. And so if you'll indulge me, I'm going to try a little experiment and share some original music with you. Give me just a minute to set it up. Okay, so this beat comes from that particular rhythm. So E4 beats per minute because of that particular pulsar. The device that I have over here is called a Leslie cabinet. The bass player in my band built this Leslie cabinet himself. And the way a Leslie cabinet works is I've got some speakers in here, and the speakers can spin around. And so the way they spin around, that means that you're going to get blasts of sound and then no sound, blasts of sound and no sound when I have this going on. You're also going to detect that the frequency tends to go up and down and up and down, and that's Doppler shift. And you'll even see more of a distortion of the sound because of the Doppler effect and because of this shifting of the sound being towards you and away from you, kind of like what a pulsar does, as I get to the last part of this. And then there are lyrics. I'm not a writer, but I like to play one on PD. So all you English majors, give me some grace. And I'm choosing some minor chords and some major chords. Sometimes life just feels lovely. And there's nothing more that tells me. I just wanna get away. On my keyboard and I play the pain, it's sharp and bright. Then I open my soul until it lets in the light of my spirit. It's grounded in the beat. Let my voice ride and my song is complete. Play my anger, play my pain. Oh, and let the sun come out. I'll play the rain. I'm on it to the center of a soul crushing cycle. From an open horizon, the radiation rose from the pillars and taken back. Something's lost, something's gained. I emerge a little stronger and begin again. Words and spoke benign and mean. Make me feel that I'm unseen. So that I and I'll look you in the eye and call your bluff. Play the chaos at the fear. You're the mother of my sisters, and there was only conflict. I need my for a journey to my future from my past. I'm a just like a stardust, and I'm built to last. Play my courage, play my hope. Go on, tell me I'm too much. What should we expect? Supernova, brighter than a billion lights. From the mountain, no matter. A new star will soon shine bright. And in a new story, something's lost and something's gained. I emerge a little stronger and begin again. I played my courage, I played my own. Go on, tell me I'm too much. What you expect? I go supernova, brighter than 1,000 lights. From the wreckage and the matter, a new star will soon shine bright. And in a new familiar story, something's lost and something's gained. I emerge a little stronger and begin again. Anybody have any questions?
When's your album come out?
You want to be my manager?
Yeah, I've got a quick one.
You can do my album cover.
I'll do that.
Did you have a question?
Yes, I was wondering, in the Grand Nebula,
I was wondering, you said it's really bright when it goes supernova. I'm
Yes.
wondering how long that lasts.
It depends on the supernova. There was a supernova in 1987, supernova 1987A, and it was appreciably brighter for months. So you went from something you couldn't even see it. Didn't seem like there was anything there, and then boom, there was a bright object in the sky, and it was hard to miss. But again, it depends on the mass. Some of them, the brightness can last maybe a month. Some of them, it can last even longer. But there's another piece to this. The kind of supernova I told you about today is the kind of supernova that happens when a high mass star collapses. There's another kind of supernova that can actually stay brighter longer, and then it can repeat and blow up brighter again. That's called a supernova type 1. And that happens when you have two stars that are together, a binary star system, and one of them dies before the other. And so one steals matter from the other until, even though it's a dead star, fusion ignites on its surface and it blows up really bright. And if it does that a few times, it will accrete enough matter onto its surface so that it will go supernova. And it has a different brightness signature when that happens. But yeah, depending on the supernova, it could last a few days, it could last a few months. But typically there's a real high brightness, and that lasts for a short period of time, then it plateaus. And it's way brighter than it was, but not as bright as it was when it peaked. And then it starts going off slowly. But yeah, I mean, it's feasible that it could last for, at some level of more brightness than it had before with supernova. That could go on for a year. Yes.
While we're on supernova, let's for a moment fantasize my spaceship has crossed the event horizon and I'm sucked into the supernova. What then happens?
Well, if you're sucked into a black hole, bye-bye, see you later. And there are some other bad things that are going to happen to you before you even get to the event horizon. But if you are in the vicinity of a star that goes supernova, you're going to have a lot of material that moves out in all directions. In close proximity, it's probably going to rip you apart too, because we're talking about a lot of pressure and a lot of matter that's shooting out in all directions. But the other thing is space is so big, if you're far enough out, it could be that the amount of matter that hits your area of space is very little matter. Sort of like when it comes to some of the interstellar matter that is really, really hot, interstellar matter, there are very few particles in there. So even if it's 7,000 Kelvin, if you stood in it, it's 7,000 Kelvin because of how fast those atoms are moving around. But there are so few of them and they're so far apart, that's probably not going to have very much of an effect on you. So what I'm saying is if you're far enough away, it could be that the amount of matter that ends up at that point is not enough to do you enough damage. But if you're very close, even the little stuff is going to hit you really hard and probably tear your ship up.
Thank you.
Don't go there.
I won't.
Any other questions? Yes.
What's your favorite nebula?
My favorite nebula, the Butterfly Nebula.
That one's dry, that one.
I think the Butterfly Nebula is just beautiful. Beautiful colors, kind of looks a little different. I mean, don't get me wrong. I think that the Eagle Nebula is beautiful and I love the Pillars of Creation and all that kind of stuff, but the Butterfly Nebula is just artistically. Yes. So, any other questions? Yes.
There's a whole subgenre of ambient music going on right now called space ambient. Have you listened to it?
I haven't. I haven't
Especially
listened to space ambient.
it's usually all synthesizers. It's very meditative, but there's a really cool band called Hovercraft that I would recommend this. It's very drony. It's 22-minute ambient synthesizer music, but there's a huge genre of it right now. It's really worth listening to.
I will definitely check that out. You said the band's name is Hovercraft.
Yeah, they're from Germany, so I think it's spelled a little differently.
Okay.
But yeah, it's
Hovercraft from Germany, and then you said that the kind of music is
I call it
Space-
space ambient, so it's
Space
very ambient, usually just synthesizers, but very meditative, very, very cool.
That sounds wonderful. Thank you for telling me about
Absolutely.
that. Any, yes,
Yeah, so what do you know about Gliese 710?
about the what?
It's a star and it's moving directly in our direction, we think. And I don't know about the timeline, it's very far into the future, but we think it'll come within the Oort cloud. So I don't know. That was just the thing I was thinking about here, like what happens,
What happens if that
Yeah.
star comes within our Oort cloud?
It's way if the in the future,
Yeah,
like
yeah.
there won't be humans, but
It's not unusual. There are stars that move toward us. This one is probably just closer, and so they're concerned about it. The nearest star to us right now is 4 light years away, which means that if you go out and look at Alpha Centauri tonight, you're gonna see it the way it was 4 years ago. So it took 4 years for that light to just get here. This star is
further out.
farther out than 4 light years away. So we do have some time. Lots of things can happen to stars. They form little partnerships along the way all the time, but if it does come within our Oort cloud, then it will disrupt the orbits of planets. It will definitely disrupt the orbit of the Oort cloud, the Kuiper belt, and so we could see, first of all, comets acting much more erratically than they do. But space is big, Earth is relatively small, we might not get hit, but if Jupiter gets hit, and Jupiter is bigger than we are, Jupiter really stabilizes our planetary system a lot. And so if anything happens to Jupiter or even Saturn, they really save us from a lot of debris in space. And so if they're not there to do that, we're gonna be in worse trouble. So, but yeah.
thank you.
Yes,
If you'll let me change the subject slightly a little bit, have you read anything about, 3I Atlas comet? And if you have, what your take is on that?
don't know very much about that particular comet. Comets in general are either long-term or long period comets or short period comets. Short period comets come out of the Kuiper belt and they stay kind of in the same disk that the planets do. The comets from the Oort cloud is a spherical region that surrounds our whole solar system, internal solar system, and it's bunches and bunches of minor planets and comets. And the comets that come from there, it takes them a longer time to go around, but they haven't been around as many times, which means they got a lot more matter in them. They pack more of a punch, and they can come from any direction. So they can come from up above the plane of our planets or down below, or so that would be harder to calculate what was going to happen. Do they think it's on a collision course with us?
Well, from what I understand, it's heading toward us, but it has time to dump because the I think it's what do you call it? The molecular or chemistry makeup is different than what they see in most comets.
Oh, that would be interesting.
So, I mean, there's one guy from some university that's saying it's a UFO mothership coming to introduce themselves.
I could tell you, but no.
That's what I thought.
One of the, this is, kind of related to what we were talking about today. Back when I first started studying physics and astronomy, and we still use the Drake equation to figure out how probable is it that there are other stars with intelligent life that can communicate with us in our galaxy and so on and so forth. And back then, I would calculate it for my students and the odds were so low. Then in the 80s, they started discovering more and more extrasolar planets. So planets that were around other stars. And so I had to up that part of the equation. We've also found that even in these star forming regions, it's not just atoms that exist there, there are molecules that exist there, and sometimes there are organic molecules that exist there. So carbon molecules that are building blocks of the kind of life that we are. And so over my lifetime, and we're gonna pretend that's about 21 years, the likelihood of there being life besides us in our galaxy has gone way, way up. So I'm not saying that that comet is a spaceship and the aliens are coming for us, or even if they would like us, they might come by and say, kids, roll up your windows. We're going through the bathroom today. Lock the doors, lock the doors. Don't let them get the hubcaps, but that might be too far, but I have seen that the chances in the equation go up quite a lot in my lifetime. And I think that with James Webb Telescope and IRAS and all of these other different telescopes, and even with that black hole picture that you saw, it wasn't one radio telescope, but it was radio telescopes that ranged from South America, from the South Pole to Spain. And they formed, you know, kind of like the Power Rangers, formed one big Power Ranger. All of these smaller radio telescopes formed one big radio telescope that simulated a radio telescope as big as our entire planet. And when people work together and they do things like that, we can discover all kinds of things. And maybe somebody will want to come play with us. Any other questions?
So I've always been fascinated by the size of everything, like how Sirius and Betelgeuse are absolutely massive. Like ton 618 being bigger than like our solar system being a speck to like what do you think of as how the sheer scale of those things that exist? I think it's unfathomable how massive they are. I guess like the massive isn't even the right description. They're bigger than our solar system, like galaxies. It's crazy.
Absolutely, it is crazy, but it's phenomenal. And that we get to be a conscious part of all of this, I think is really phenomenal, and we should appreciate that. But yeah, I don't think that I mentioned this to you all before, but when it comes to interstellar matter, we think of the space between stars as being a vacuum. And it is better than the vacuums that we can produce in a laboratory here most of the time. But there are still particles there. There are particles of gas, there are particles of dust. Now, there might only be a few of them in a cubic meter, but they're there. And space is so vast that if we took just the interstellar matter, that gas and dust, and we looked at that and we drew a sphere around our sun that was 1 light year in diameter. So our sun, we don't even have to count the planets in this. Our sun, and then we draw a sphere around it, 1 light year in diameter, and we just pick up all of the interstellar matter, all of those atoms and dust particles that are very, very spaced very, very far apart. There would be enough matter for us to make another sun. That's just within that 1 light year sphere. So if we went all the way out to the next closest star to us, 4 light years away, that's even more. Another interesting thing is, some of you seem to be really interested in disasters happening and stuff. So let me tell you the good side of some disasters. We definitely know that the galactic galaxy clusters in our universe are moving away from each other. And it's really not so much that they're moving away from each other, but the space between them is expanding. And so that is totally cool and totally different talk. But we have all of this going on, but sometimes these galaxies, because they're orbiting each other in these complicated ways as well, they can run into each other. And you might have 2 galaxies that come together. And when 2 galaxies come together, it's a cataclysmic event. But it's a cataclysmic event that takes the gas and the dust that's hanging out in these galaxies, and it smushes it together. And when it smushes it together, you get dense pockets of gas and dust. And when you get dense pockets of gas and dust, boom, 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 star formation. So you get starburst galaxies from this cataclysmic thing that's happening. Also, when new stars are born, it's very energetic. It can cause the interstellar matter around it to create the birth of stars because of its energetic birth. And when stars go supernova, even if it's farther away, they can cause gas and dust far away from them to come together. And when it comes together, that supernova can be the thing that sparks new stellar formation somewhere else in a galaxy. But very, very fascinating. And as far as the biggest thing, we've got our sun, our planet. I already told you that you can fit more than 1 million Earth-sized planets into our sun. And our sun is like, has about 99% plus the matter in all of our solar system. Then you move out from there, we are in a galaxy that contains about 400 billion stars. That's billion with a B. 400 billion stars. And our galaxy is one of 30 galaxies in a cluster called the local group. And our local group is part of the Virgo supercluster, which contains not thousands of galaxies, but thousands of galactic clusters. Our galactic cluster is little, with only about 30 galaxies in it, but the Virgo cluster has thousands of galaxies in it. And the Virgo supercluster is only one of many superclusters in our galaxy. And so when Carl Sagan said billions and billions of stars, he was underselling it. I mean, space, the universe is incredibly huge, which means that there's lots to find out and we'll always have something to do. Any other questions? Thank you very much for indulging today. I wish you is that you will always see yourself through the eyes of the people that love the authentic you best.
Thank you.